Let's talk about density. So what is density? Have you heard that word before? It's what? It's how dense something is? It's true. It's not necessarily the most helpful definition, but it's true. Thank you. It has to do with something about particles, but that's actually way down more on the atomic scale. If we were to say kind of in general, what is density a measure of? If we say that something has a density of 1 what? What does that mean? What does that have to do with anything? You know? What? It has to do with mass. Yes, so we'll first look at the math equation of it, which is mass divided by volume. So yes, that's how you calculate density, is you take the mass and you divide it by volume. But what is it? What does that mean? What does mass over volume mean? The what? I guess that could relate to it, but that would be more on a specific situation. We're looking for something a little bit more general, but yeah, I could see that. What does it mean for something to have a certain amount of mass and a certain amount of volume? Maybe think about this. It's kind of a little bit of an abstract concept. Mass is related to weight. It's sort of how much. It's related to size as well, although we can define those in a couple different ways. Mass is really how much matter something is, how much stuff there actually is in it. So we're going to define density as the amount of matter in a given amount of space. Mass refers to how much matter something has, and volume refers to how much space it takes up. So this gives us a relationship of how much stuff is there in a certain amount of space. And usually that given amount of space that we're talking about is 1 milliliter. When we ask about the density of a substance, we're usually asking about how much stuff is there, how much matter is there in 1 milliliter volume of this stuff. So something that is very dense means 1 milliliter of it is going to be very heavy. Something that is very much more less dense means that something that 1 milliliter of it is going to be quite light. The standard unit for density is grams per 1 milliliter, or grams per 1 cubic centimeter. A cubic centimeter is the same as a milliliter.
I forget what the 3 is.
The 3.
Wait, is that?
Cubic, so that's a cubic centimeter, a centimeter cubed. This is also known as cc for cubic centimeter. You might see that on a syringe or something, so many cc's. That stands for cubic centimeters. And that's the same as a milliliter. You might also see this written in this kind of slash notation. Means the same thing. When we see that kind of a unit put on the end of a number, we have to recognize that that actually means the same as this. So let me give you an example. The density of water at 4 degrees C is 1.00 grams per 1 ml. It actually changes a little bit with temperature, but that's what it is at 4 degrees C. So that means that 1 milliliter of water at 4 degrees C weighs exactly 1 gram. Another way of writing that you might see is something like that. Just because it's easier to kind of write it in line like that sometimes, or if you're typing. So you'll see that, and you have to recognize that this actually means the same thing. This, so that's the same. This is a lot more obvious of how we would use that in like a unit conversion or a calculation. This is a little bit less obvious. So we have to recognize that those are actually the same, and we can rewrite this as this.
Is that the density?
Yes, so this would be the density of water at 4 degrees C. And today in lab, you're going to measure some densities and calculate some densities and try to figure that out. So why might we want to know a density of something? What information does that tell us? Why do we care about the density? Has anybody here ever measured the density of something? What'd you measure the density of?
It was in chemistry class in high school. It was just like of water.
Okay.
Particles, and we just stacked them on top of each other.
And figured out the density. Has anybody, okay, yeah, that works. And that's kind of like what we'll be doing in lab today. Has anybody measured density in a non-chemistry class setting? Has everybody ever heard of density being measured in something for some reason?
No, but I am confused about something there.
Okay, what are you confused about up there?
Okay, density of water, 4 degrees Celsius, how does that relate to 1 gram, 1 milliliter?
That tells you that water at that temperature, 1 milliliter of it weighs 1 gram. That's what the density tells us. How much does a certain amount of volume weigh? Or how much space does a certain amount of mass take up? So a couple of things that come up in measuring density, or that may come up in measuring density. One is that this is a really powerful way to convert between two things that aren't really the same type of measurement. Normally when we talked about a unit conversion, it was like grams to pounds or to ounces or something like that, where we're using the same kind of thing. We're always measuring mass, just in different scales. Now we have a way to make a connection between mass measurements and volume measurements. The reason that's important is because sometimes it's easier to measure one or the other. And if you know the density, it doesn't matter how you measure it. If you're trying to, let's say, check a measurement apparatus, like this happened to us a few weeks ago. One of my kids had to take some medicine, and amoxicillin, you know, the like pink bubblegum kind of weird stuff. And he needed a teaspoon, which is 5 milliliters of it. And we had this old kind of medicine spoon that looked like an alligator, and he liked to drink out of it, but we weren't sure how accurate it was. And so one way we could test that accuracy, and this is actually what we did, was we took the spoon and we put it on our balance at home, and we filled it up to the line with water at 5 mLs and saw if, well, does that weigh 5 grams? If it does, then we knew it was right. If it didn't, then we knew it was a little bit off. So we could standardize it in that way. So that's one way. You're all looking at me like, you're just a huge nerd. Nobody would do that. but that's how we did it. And we were able to confirm that, yes, this 5 milliliter line and this little alligator thing is actually in the right spot. And it is delivering the amount of medicine, or it would have delivered the amount of medicine if you didn't just kind of spit it all over us all the time, because he's little and that's what they do. So that's one way. Other ways that it comes up in health fields are things like bone density. Have you heard of bone density measurements? Where is that important? Or why is that important? The what?
It says the density of your bones determines their health and strength.
Yeah. Okay. Has anybody ever done or like assisted with a bone density measurement or anything like that? It's one of the things is to check for something like osteoporosis, which is where the bones become more porous. They have holes in them. They get small holes in them later in life, and that can make them much weaker. So you can check the density, and if they are less dense, that means they have less matter in the same amount of bone. And so if there's less matter in that bone, it's not going to be as strong. There's less stuff in there, and then they're more likely to break more easily. So you might have the density of your bones checked to see that. What? Well, that can be a way to measure it, but no, it's more about how much mass is within that bone. Yeah. Because the holes actually are
What's the mass
inside the bone. It's mostly a calcium salt. Yeah.
If somebody's referring to like having big bones, does that mean they have just like a ton of matter in them? Or?
I'm not sure that's actually a real thing. I think it's more of an expression.
I took like a diet course, and there was this nutrition counselor, and she said she had a client who actually had like heavy bones.
Yeah, that's certainly reasonable that you could have more dense or less dense bones, and maybe some people have like super dense bones. Yeah.
Does that occur with any health issues then?
I have no idea. Anybody know anything about heavy bones?
Well, wouldn't
Like extra heavy
osteoporosis
ones?
mean that you don't have heavy bones?
Right, it's the opposite. So I don't know what the corollary to that is if your bones are too heavy. I don't know. We could look it up. So let's talk about how we use density to make some of these switches back and forth between different systems. So one thing we might be able to answer, let me look at this picture, or let me show you a picture. It's about the most I can get on the computer here. This comes from the book. What you see here, there's a little picture up here of a beaker full of water with some stuff in it. There's a cork, there's some ice, the water is the liquid, and then there's aluminum and lead kind of sitting down here. And the densities of each of those are given in grams per milliliter. So based on the numbers that you see here, and then what you actually observe happening in this water, what can you say about the density? What can you say about how the density helps you predict some behavior? Yeah, so we can say that things, exactly. So those items here where the density is lower than that of water, remember water is 1, so the ones that have a density lower than water are going to float, and ones with a density higher than water are going to sink. And we can even see a little bit more than that the ice kind of, just the edge peaks out a little bit, and you can see the density is very close to that of water. Whereas the cork is much, much lower density, and so it almost sits kind of on top of the water. And so you can make some conclusions about whether a solid object will sink or float in water based on its density. Here are some other densities of common substances. You'll notice not just liquids have density, but you can measure densities of solids. There are some really low density solids like cork and wood, and then high density solids like aluminum, diamond, and there's some that I cut off like lead and stuff like that. You can see that has a really, really high density. Yep.
What is the density? Never mind, I just answered my own question.
Okay. Then you can some liquids. You can see some liquids. One interesting thing that kind of we get turned around in our head sometimes is oil and water. Have you ever poured oil into water, or you've seen oil in water? Where does oil go? Does it go on the top or does it go on the bottom? It goes on the top. And that tells us that oil has a lower density than water, which is what we see here. Sometimes people get that a little bit turned around because oil seems very thick and heavy. Like we think of oil as being thicker. And that's a measure of something called viscosity, which is how well it flows, but it is not related to the density. So something can be very thick and hard to flow, but still be low density, and that's what happens with oil, and that sits right on the top of the water. Gases also have densities, but they're so much less dense that we measure the density in a different unit. So these gases are given in grams per liter rather than grams per milliliter. If we wanted to have these in grams per milliliter, we would multiply this by 1,000. So their densities are much, or I'm sorry, we would divide them by 1,000. So their densities are much, much lower than the densities of liquids or solids.
Everything over 1 is higher density?
1 gram per milliliter, right? It would be higher density than water. These, like air, the density of air is 1.29, but that's grams per liter. So that's actually 0.00129 grams per milliliter. I think they should have kept them the same units, so it's easier to compare them on this table, but that's how they decided to do it, so whatever. All right, let's look at a calculation with density. One thing that you should know with density calculations is it's not different. It's not different from the stuff we've already done. It's just another way to use these units. So let's imagine that we have 2.0 teaspoons of a cough syrup whose density is 1.20 grams per milliliter. And the question is, What is the mass of the cough syrup? Now, it sounds like kind of a different question because rather than asking for a unit, it's just saying, what is the mass? But really, it's the same type of question. We need the same kind of a roadmap. We need to start with some kind of unit and then end with some kind of unit. In this case, since we're being asked for mass, we're going to end with grams. It's going to be our unit that we end up on. And the thing we want to start with in this case is the 2 teaspoons. That's what we're given. So we're given teaspoons and we want to find grams. How do we have any number here that tells us about a relationship between teaspoons and grams directly? Do you see anything in the problem?
Well, the density.
The density tells us the relationship between grams and milliliters, but it doesn't say anything about teaspoons, right? So yes, the density tells us that we can go from milliliters to grams, but it doesn't tell us directly about the teaspoons. So we're going to need another step to go from teaspoons to milliliters. And that's a number we'd have to look up. Does anybody know how many teaspoons are in a milliliter or milliliters are in a teaspoon?
5.
5, right. There's 5 milliliters in 1 teaspoon. So 5 milliliters in a teaspoon, 15 milliliters in a tablespoon, and 30 milliliters in an ounce. So now we can go from teaspoons to milliliters to grams using these quantities. Let's set this up the same way we set up those other problems last week. We'll start with the 2.0 teaspoons and just put it over 1 with no units. And then we want to get rid of teaspoons based on our plan and go to milliliters. And then we get rid of milliliters and go to grams. And that will allow us to cancel teaspoons, cancel milliliters, and our final number will end up in grams. As long as we follow the units through, we'll get the right thing. So let's fill in our numbers. Our equivalence up there to the right tells us that there are 5 milliliters in 1 teaspoon. And then our density tells us that there are 1.20 grams in 1 milliliter. So we multiply through those. 2 times 5 is 10. 10 times 1.2 is 12.0. So our final answer is going to be 12.0 grams of cough syrup. All right, so same type of question as what we did last week, except we're adding this density term at the end here to go from from milliliters to grams. All right, we did that one together. Now you try one. Yeah.
Okay, I get why it's 2.0 teaspoons over 1. But is there like any type of rule about the order? So could you do 1.20 grams over 1 milliliter before the 5 and 1?
Yeah, it doesn't matter what order you do it in. The reason that we do it in this order is so we can kind of track the units. So this one cancels with this one, and then this one cancels with this one, and then we're left with grams. But yeah, you could do them in the other order also. Should be the same. All right, have you heard of a glucose solution? Yeah. A glucose solution has a density of 1.15 grams per milliliter. In general, adding sugar, dissolving sugar in something is going to increase the density because now you've got more stuff in about the same amount of space. In fact, you may have heard, does anybody here do any fermentation, like brewing or anything like that? Or if you know anybody who's done that. If you ever do that at home, if you want to make some wine or beer or whatever, one thing that they'll often do is measure the density before the fermentation starts, because the amount of sugar that's in that initial batch determines the amount of alcohol that you have in the end product. So if you know the density, which they call the specific gravity, but it's the same thing, of that initial stuff, after it ferments, you know how much alcohol you're going to have because of how the sugar affects the density. So anyway, it's kind of an aside. Let's say we have this glucose solution. with a density of 1.15 milliliters. And we want to measure it out. Oops. Before I ask that, we need 575 grams of glucose solution. How many liters is that? So you need 575 grams. You're given a mass of glucose solution that you need to measure, but glucose solution comes in like bags or jugs or something. So a lot of times with liquids, it's a lot easier to measure it in volume rather than in mass. So if we have 575 grams, and we want to know how many liters is that, we need the density. So start with that 575 grams and see if you can come up with one of these plans again of how you can go from unit to unit to end up in liters. And if you could set it all up, go ahead and put the numbers in and try to calculate it out on your own. I'll give you a couple minutes, and then we'll look at it together. I'm just going to wander around and kind of see how your setups look. Remember to follow the units. So if you start with grams, think, well, what can I turn grams into that gets me closer to my answer? And then what can I turn this next thing into that gets me closer to my answer? And so on. Remember to follow the units here. So this part is closer, except that there's 1,000 liters. But same thing here. I think you got to turn the track with it's flipped. So make sure you only write all the units out so you can see if they actually. All right, look like some good starts to this. Again, I'm going to emphasize or encourage you to follow the units. So we start with that 575 grams, which means our first unit is grams. Our end unit is going to be liters, right? Because that's what it asks for. So how do we get from grams to liters? That's the question. What can we get from grams to that gets us closer to liters? Milliliters, right, exactly. We can use that density to go from grams to milliliters. And then can we go from milliliters to liters, or do we need another step in there? We're good. We can go from milliliters to liters. So let's set up that expression now and see if we can follow those units through. So we'll start with the 575 grams. And then we want to convert that to milliliters, which means grams go on the bottom, milliliters go on the top. Then the next step, remember, we're going to do all our units, make sure everything's in the right spot before we put the numbers in. So now we've canceled out grams. Now we want to cancel out milliliters and get to liters. So with grams and milliliters, now we can fill out our numbers. Grams to milliliters, our density tells us that through our 1.15 grams in 1 milliliter. And this type of a problem is why that using the units like that can be so important. We can't just say, oh, we multiply by the density. Because, yeah, it's true, but we multiply by the upside down density, right? Because we want to cancel grams and end up with milliliters. So if you follow the units through, you'll have less of a chance of putting that on the wrong side. Same thing between milliliters and liters. We know maybe that there's a number of 1,000 in there somewhere. Is it 1,000 milliliters in a liter, or is it 1,000 liters in a milliliter? Yeah, 1,000 milliliters in a liter. How do you know, or how do you remember that? Well, which one's smaller, a milliliter or a liter? A milliliter. So everybody seemed pretty sure about that. So if you just remember which one's smaller, there's got to be 1,000 of the smaller one and the bigger one. There's not going to be 1,000 of the bigger one and the smaller one. As you work in lab and as we get some more experience, you'll have some experience to look at with this too. You know that when you measure out a milliliter in lab, it's like that much. And when you measure out a liter, it's a lot more. Okay, so we do that, which means evaluating this expression means multiplying through everything on top, dividing by everything on the bottom. And that's going to come out to about 0.5. 0.5 liters. If you didn't put those extra zeros, that's okay. We said we weren't going to worry too much about how many decimal places we use in this class. So about half a liter is what you'd need to get those 575 grams of glucose solution. All right, so once again, that's using the density. It's not different. It's the same technique. We just use another factor, and density allows us to relate mass and volume. So grams and milliliters generally. Yep.
How come when I went over the tutoring center, he had no idea why you were crossing out the grams and milliliters and milliliters? I was like, who was doing this? He said I was doing it wrong.
I don't know.
Oh, okay. I just didn't know if this is a simplified way of explaining it, or if there's something I'm missing. Okay.
I don't think so. This is the way that we've usually done it. I mean, it's true that there's other ways to evaluate these.
This isn't a typical chemistry course, so
Yeah.
I didn't know
But-
if this
but-
is a simplified way or. if
Not
it's
really. Yeah,
different
converting
for-
units is converting units. This is the same.
So it is,
Should be all the way through. Yeah.
so, or canceling out the milliliters and grams is how
I
you
think
figure
so.
it out.
Yeah. That's how I would do it. Yeah.
How did you get that 0.5?
You take that 575, divide by 1.15,
Oh, okay.
and then divide by 1,000.
So I did it.
Yeah.
No, I did that exact thing, but I just flipped the numbers. I did that
Right.
exact thing.
Yeah, and that's the most common way of being wrong with these, is just having a number flip somewhere. So the way to not have the numbers flip is to think in each of those relationships, how many of these and how many of these. We know from the density it means 1.15 grams in a milliliter. We know from the metric equivalences, it's 1,000 milliliters in a liter. So if you keep track of the units and do it that way, that should keep you straight.
Okay.
So I have a question, just to make sure. So we have to multiply 575 by 1 and then divide by 115, or multiply again by 1 and then divide?
Doesn't matter.
It makes difference.
It only makes a difference if you, depending on your calculator.
When you multiply the 1.15 times 1,000.
So I have to do
Yeah.
it step by step, like I have to multiply first the highest row and then the lowest and then divide.
That's one way to do it. That works, yes.
Mhm.
You can also do it in order, but depending on your calculator.
Yeah, because when I calculate, it shows me different.
So how did you type it in? If you don't mind my asking.
Like
So you can check.
575.
Yep.
First, I multiplied the highest and then the lowest. So when I multiply 115 on 1,000, it shows me 1.150. And then I divide 575 on 1.150.
Oh, that would be 1,150, right?
Yeah, it shows me this. Yeah.
So there shouldn't be a decimal there.
Yeah, but it shows me decimal, so that's why I'm asking.
Maybe there was an issue in the way you pushed it in, because that should work out. If you multiply 1.15 times 1,000, you should get 1150 with no
Yeah,
decimal in the middle.
It shows me.
And then if you divide 575 by 1150, you should get 0.5. So I'm not sure if we can maybe look at that later, but that shouldn't matter.
On a test, if we don't put the additional zeros.
It doesn't matter. All right, so that's some density. All right, let's look at some matter definitions. I'll start a new thing here because this is really now the next bit. We're going to set up a little tree. Not like a real tree, but just, one of those things that kind of branches down like a family tree, sort of. About matter. Matter is stuff, material, whatever everything is made up of. Something that has mass and takes up space. That's matter. We're going to split matter up into two categories. Those two categories are the pure substances, and what do you think the other category is? Yeah, if it's not a pure substance, it's a mixture. So the mixtures. If we're further going to break this down into a couple categories before we go through and define them. Pure substances can be either elements or compounds. And mixtures can be either homogeneous or heterogeneous. So we have pure substances as mixtures, and we have elements, compounds, homogeneous mixtures, heterogeneous mixtures. Anybody feel good about defining one of those or giving some idea of what one of those is? Yeah.
Pure substance would be H2O.
A pure substance, an example of that would be H2O. So what do you think of as a definition? What makes something a pure substance versus a mixture?
There's no, by itself, like those are pure substances and are elements of pure one thing. Compound is a combination.
Okay.
They're compound word.
All right. So we can start over there. So like this fits with your water definition as well. That elements are made up of one type of atom. And then compounds are two or more types of atoms that are chemically bound together. So that would be water, for instance. So an element might be H2 or O2, which is hydrogen gas or oxygen gas. We'll talk later in the semester about why it's the two. A compound might be H2O, as you said, water, because it's made up of two types of elements, hydrogen and oxygen, but they're chemically bound together. And the importance of them being chemically bound together is that they can only be separated through chemical means, meaning you have to actually change what that water is to break it down and make it into something else. So looking on the other side then, what do you think about those two types of mixtures? Have you heard those words before, homogeneous or heterogeneous? What do they mean, or how do they apply to mixtures? Anybody want to give that a shot?
Something that can be taken out, the others now. Heterogeneous is something that can be taken out, water and coins,
Okay.
pennies.
Yeah, so you can think about it as you can clearly see the different parts of the mixture, right? That's kind of what distinguishes homogeneous from heterogeneous. Can you determine different domains in the composition, or is it all uniform throughout the whole thing? That's the phrase I usually like to use here, is that a homogeneous mixture would have a uniform composition, so it'd be the same throughout the whole mixture. And our heterogeneous mixture would be not a uniform composition. All right, so let's get some examples of these, because I think that helps us also. You already offered like pennies in water. If you had a beaker full of water with a bunch of pennies in it, that's a mixture. It's a mixture of pennies and water. But you can clearly see where the pennies are and where the water is, right? So that makes it heterogeneous. What would be an example of a homogeneous mixture? Coffee, yeah. That's a good one. But what's in coffee? Has anybody ever had coffee? It's pretty good. What's in it? Cream, maybe? What's the biggest part of coffee? Water, right? Coffee is mostly water. But then, yeah, you've got caffeine, you've got all these flavor molecules, you've got color molecules because it's kind of brown. All that stuff is all mixed up in there. But you can't separate those parts. You can't say the water in the coffee is here and the caffeine is here and the flavor is over here like you could with the pennies in the water. So that would be an example of a homogeneous composition or a homogeneous mixture. What else? Let's try to populate all of these with some more examples. So somebody give me an example, and then where would you put it in these categories?
Sorry, I wasn't listening. What was your question?
What's an example of some matter, and which category does it fit in?
Cereal.
Cereal. Where does cereal go?
Hetero.
Heterogeneous? Sure. Any kind of cereal in particular you're thinking of? Say anything?
What can you say about like iced water?
So water with ice in it?
Yeah.
What do you think? Water with ice in it.
Elements?
Okay, say the
No,
water
it's
hasn't
still an
melted.
element. You know what I mean? I know it's still a compound, really. H2O, just in a different form.
But it's just water, yeah, it's different.
Yeah,
Liquid and solid.
State.
It's temporarily solid.
sure. So you could really put this in a couple categories, I would say. I think that you're all right, that it's all H2O, assuming it's pure ice and pure water. It's all H2O, so it's a compound. But it's also a heterogeneous mixture of solid water and liquid water, and you can clearly tell the difference. So where does it fit? I don't know. These aren't necessarily strict categories. I think we can think of a lot of examples where, depending on our frame of reference or how we think about it, they might fit into one example or one category or the other.
So where would you put carbonated water or anything carbonated?
Anything carbonated, what do you think? Homogeneous mixture? Why?
Because you can separate it.
You can't separate it.
Yeah, well,
So you could-
what if it's carbonated water? It's a compound, but again, it's temporarily a gas. Like that, it goes flat, right?
Yeah. So are we talking about it while it's carbonated or while it's flat? That might change the answer. I would say, here's how I would think about it. I would say carbonated, let's say soda, let's say Coke. Anybody know what that?
No, both
Is?
can be homogeneous, but it has colors.
Yeah, so we've got colors and flavors and sugars and things like that. But the bubbles, the fact that it has bubbles in it, I would say that kind of pushes it into the heterogeneous category, right? Because you can see where the bubbles are and where they're not. You can clearly see different domains. Here's bubbles and here's not bubbles. If you let it go flat, it doesn't have those bubbles anymore. So now it's probably in the homogeneous category. And with water, if we said carbonated water, well, while it's carbonated, while we see the bubbles, probably goes in the heterogeneous category because we see the water and we see the bubbles, which what are the bubbles made out of? CO2, right? Carbonated, carbon dioxide. So we see water, we see carbon dioxide. Those are different compounds that are together. That's probably a heterogeneous mixture. But then again, if that water goes flat, then it's just water, so maybe it's back to a compound. Or if you really want to be really fancy, have you ever tasted carbonated water after it goes flat? It still doesn't quite taste like water, right? Because there's actually some other stuff in there. The carbonated water, some of that carbon dioxide is actually dissolved into the water. And so that's still there, even though it's no longer bubbling, actively bubbling. So that might be more like a homogeneous mixture. So you can see these categories get a little bit fuzzy depending on what you think about. Some things very clearly fit in one category or another. Some definitely don't. So let's think of, can anybody think of a homogeneous mixture that is not a liquid? Ice cream. Sure, yeah. Depending on the ice cream, right?
Yeah.
Some ice creams might go into that heterogeneous category depending on how many nuts and whatever in there. So that's okay. We'll say ice cream.
Penny. Or our currency, like any coins that we have.
Yeah, let's just say coin. Coin, yeah. And in fact, metal alloys in general, when you have mixtures of different metals together, different elements coming together, that's going to be a mixture. Now, it's not exactly a compound because, although again, some people might argue that, but alloys will generally fit in this homogeneous mixture category.
These questions in test.
Yeah. But here's what I would do on a test. If it were like a multiple choice kind of thing where I said, which category does this fit in? It would have to be a clear and obvious one. It would have to be one that there's not really a question. But the other interesting question that I might ask is, how would you categorize these and why? And then I'm more interested in how you reason your explanation for which category they fit in, rather than are they in the right category? Because as we talked about, some of them kind of fit in different categories. Other solid homogeneous mixtures, things like steel, like the steel that your cars are made out of. What's the main component of steel? Anybody know? Iron, yeah. Steel's mostly made out of iron, but there's a lot of other stuff in there too. There could be chromium, nickel. They give it all different properties depending on what else is mixed in. So that would be considered a homogeneous mixture because when you look at steel, it all just looks like the same thing. You don't necessarily see those different domains. Another interesting one that kind of fits in across some categories, blood. Where would you put blood?
Heterogeneous. Heterogeneous.
So who says heterogeneous? Who says homogeneous? Yeah, it kind of depends on how you're looking at it. If you're looking under a microscope, it's absolutely heterogeneous. Even if you just kind of bleed out onto the table and let it sit there for a little bit, it's going to start looking different, right? You're going to see the platelets coming together, and you're going to see the cells, and there's definitely different domains. But if you just have like a big jar of blood, that's going to look pretty homogeneous, right? If it's like, I don't know, if I just cut myself and start spraying blood everywhere, it's just going to look like blood. You're not going to be able to see different cells in it. So that might fit in that other category as well. So your frame of reference is going to influence how you might categorize these. So what do you think? Can you do that and categorize those?
More compounds.
Yeah, how about some more compounds? What else can we put in that compound list? So these are pure substances, but made up of multiple atoms chemically bound together.
Salt.
Salt, sure. Salt is a chemical compound made up of sodium and chloride atoms. If we break salt down into something that is not salt, so obviously we can like grind salt and that's still salt, but if we wanted to break the sodium and chloride atoms apart, we would be making something that is no longer really salt. So yeah, good. What else?
Carbon dioxide.
Yeah, the carbon dioxide from our carbonation example earlier. Carbon dioxide is CO2. It's made up of carbon atom and oxygen atoms. And if we break those apart, we no longer have carbon dioxide. We have some other chemical compound. So things like that would fit in there. Even larger molecules can be compounds if they kind of fit that. So something like sugar. We'll say table sugar, which is sucrose. Sucrose is made out of carbon, hydrogen, and oxygen atoms. I think it's C12 H23O11. I'm not sure about that, but I think that's right. Yeah, thanks. So anyway, it's made up of carbon, hydrogen, and oxygen atoms, a bunch of them. They're chemically bound together. But of course, there's a lot of stuff made up of carbon, hydrogen, and oxygen. So you could break that down into other compounds as well. And that brings us kind of to the next part, which is physical versus chemical changes. This also relates to what we just talked about, so we'll go back up and look at this in a second. One of the ways that we can distinguish between pure substances and mixtures is that pure substances can only be broken down. I was going to try to write it, but I don't have room. Pure substances can only be broken down by chemical changes, whereas mixtures can be broken down by physical changes or physical means. So what do you think that means that the difference between these two things are? What's the difference between physical changes and chemical changes? What does a chemical change do that a physical change does not do? Or vice versa?
It changes makeup.
Yeah, it changes really its identity. It's even deeper than its makeup. Because a mixture can have a particular makeup that we can change physically, but something that chemically changes actually changes its identity. So a chemical change forms new substances. Changes identity. Forms new substances, changes the identity of whatever it is. So you have water and you do a chemical reaction and you've made something that's no longer water, maybe hydrogen gas and oxygen gas or something. Again, it can be helpful to think about examples here. So a chemical change might be, a classic one is burning something, combustion. You have wood, you burn wood, you make carbon dioxide and water, you make ash, you make charcoal, whatever else, but you've changed that. It's no longer that same stuff anymore. You've really changed it. Or, you know, that's true for most other things. What are your favorite things to burn? What do you have? Favorite burned things? No. Wood? Cigarettes? Yeah. So that's a way that you can break something down, really change its identity. Other examples of physical changes, so burning and rusting metal would be another example. So you've got steel, which is mostly iron. The iron rusts and forms iron oxide, and you've made a new compound now that has a totally different identity to that steel, right? Steel is silvery and shiny and bends and dents, and rust is brown and brittle and breaks apart and is a really totally different thing. So that's an example of a chemical change.
Like concrete or asphalt be the same thing too? Or no?
Yeah, depending on what part of it you're talking about. So like concrete is made up of rocks and cement, which holds the rocks together. The cement part is a chemical reaction that, you know, starts with water and actually makes the stuff. Yeah. Is that the part you were talking about?
Yeah.
I don't.
Yes, I mean, it starts as like I guess a liquid or a liquid-esque.
Yeah.
And then hardens.
Right. And I think with concrete, that yes, that's chemical. With asphalt, that's probably more physical because you have to heat it up. You kind of like melt it and then you put it down, or is it also, I don't know. We need to look up some asphalt chemistry because I don't really know. Because the other part of it is the physical changes, which are, oops. Oh, I'm hungry. Microphone got that, so the whole internet knows I'm hungry. Changes in size, appearance, or state. Those would be the physical changes. Things like melting or boiling. Yeah, go ahead.
I said that asphalt would be state, because it's soft when it's heated, then hardens again.
Right.
Or concrete would also fit in that instead of the chemical change.
Yeah, I don't know enough about it to really say one way or the other.
More appropriate.
But with concrete, like you can't take existing concrete and like melt it back down and respread it, right? Once it's concrete, it's just.
Break it up and then into the rocks again and then add.
But you have to add new cement to redo it.
I think, yeah.
So I think that would put it in the chemical category. Because for something to be in the physical category means you melt it and then it hardens and nothing ever changes. Right? Like a candle, for instance. If you were to just melt a candle, has anyone ever made candles? You can melt the wax and then you like dip the wick in and then it hardens and it makes the candle. So that's not actually changing the identity of the wax. The wax is still the same molecules, still the same makeup. You've just changed it from a liquid to a solid. But when you burn that wax, now you're turning it into carbon dioxide and water vapor because after the candle's done burning, it's gone. Right? You can't make a new candle out of that. So that would be an example of other ones. And actually, physical changes can be even simpler than state changes. It can be something like grinding up some salt or grinding up a rock, right? Making smaller particles out of bigger particles is also a physical change. So when we say that these things can only be separated by physical or chemical means, these mixtures can be separated by physical means. So when we take, some of these are pretty easy, like pennies in water, you could just go take the pennies out of the water. That's a change in physical appearance or a change in whatever. That's a physical change. Same thing actually with the homogeneous mixtures, even though it's not as obvious. How would you separate the molecules from each other or the compounds from each other in coffee? You know how you could do that?
Boil it, so it can evaporate.
Yeah, you could evaporate all the water off. If you just let coffee sit, has anybody ever left coffee in an old mug on your desk or something, and then after a while it's just brown crap in the bottom and it's really gross? I've never done that. No, I've definitely done that. And yeah, so the water has separated through evaporation, and you could accelerate that by boiling it. And then you've left behind other things. And you could further separate that. There are all kinds of physical means that are that allow you to separate different portions of that. Things like filtration, distillation is a technique that allows you to separate things based on their boiling point. We're going to do something this semester called chromatography, which is a physical means of separation that separates compounds from each other. So there's a lot of different ways that you can do that, but you've not changed the identity of anything that you're separating, and that's really the key. Sound good? Okay. Not a lot of like fun problems to deal with in this part. All right, so I don't want to get too far ahead of us, so I'm going to stop with new stuff there. With our last little bit here, let's look at a problem, see if we can figure this out, just for some practice. And then on Thursday, we'll talk about energy, and that'll be the rest of that chapter. Let's convert 12 fluid ounces to cubic centimeters. This is another confusing part of the English or imperial system, is that fluid ounces are different than ounces. Ounces are a measure of mass or weight, and fluid ounces are a measure of volume. So, sorry, I didn't invent it, but it's confusing, I understand that. But if somebody just says ounces, they should be talking about the weight. If they say fluid ounces, they should be talking about the volume. So if you see on a, mind if I borrow your, I'm not gonna drink it. You can see here it says 20 fluid ounces. I should just do that as well. Do you mind if I borrow this cookie? Okay. 20 fluid ounces. So that's specifying that that's a volume in ounces. All right, so we could just look up how many fluid ounces are in a cubic centimeter, but we're not going to make it that easy. We're going to take a couple more steps here. I'm going to give you a couple pieces of information, and you're going to try to get this just from this information. I'm going to tell you that a gallon is 3.8 liters, and that a gallon is 128 fluid ounces. One other thing, we talked about this earlier, but I just want to say it again in case it's helpful. 1 milliliter equals 1 cubic centimeter. That's the same amount of volume. So I want you to come up with your plan of how you're going to go unit to unit to unit, and then set it up and see if you can do that conversion. All right, let's take a look through this one. So when we set up this plan of going through the units, you have to go with what you have. So yeah, it would be nice to just have fluid ounces to cubic centimeters. And if you were doing this at home, you could look up how many fluid ounces in a cubic centimeter and you'd get some number and that'd be easy. But when we have a multiple step thing like this, we have to think about how we're going to get from fluid ounces to cubic centimeters. So did anybody come up with a good plan, you think? Yeah? How'd you go?
The gallons.
All right, how'd you know you had to go to gallons first? Yeah, because that's what was given, right? Is that what you're...
Yeah, I was just gonna say, you have to cancel out the ounces.
Right, because you got to cancel out the ounces, and the only thing you can cancel the ounces with here is gallons, because we know there's 128 fluid ounces in a gallon. All right, so now we go to gallons. Now where can we go from gallons to get us closer? Liters, right, because that first one gives us gallons to liters. And then where? Milliliters. And then that gives us cubic centimeters. Actually, those are the same, right? So yeah, that looks like a great plan. So let's set up the fraction and see what it comes out to. We'll take 12 fluid ounces, put a 1 on the bottom because we got nothing on the bottom to worry about. And then we're going to have fluid ounces down here and gallons up here. Then we've got gallons to liters. And then liters to milliliters. And then milliliters to cubic centimeters. And we could really skip that last one because we know those are the same. But we'll just put it all up anyway. Now we fill in our numbers. The things up there tell us there are 128 fluid ounces in a gallon. There's 1 gallon to 3.8 liters. There are, this one we don't see up there, but we know this one, 1,000 milliliters in a liter. And then these are 1 to 1. So we're going to multiply that 12 by 3.8 and 1,000, and then divide by 128. What do you get? All right. Looks like a lot of agreement. That's great. 25? Yeah?
I mean, I just skipped the gallon step. Just for 3.8 liters over 128.
Yes, that's a good point. So let's you know what? That's great. I don't want to confuse everybody, so I'm not going to go through it. But yes, that works also. You can skip that. But the point I did want to make, or did want to look at, is you don't have to always have 1 on the other side of your equation. So for instance, let's do this one more time, but with a different equivalent. Same problem, but this time we're going to use, that's the soda again. Yeah, I'm not going to drink it. Just looking at it. And it says here 20 fluid ounces, 591 ml. So we're going to use that as our equivalence. 20 fluid ounces, 591 ml. Right? That would also work as a equivalence. It's not an identity. I mean, it doesn't have 1 on one of the sides of it, but it still tells us how much of this is in how much of this. If we had that, that would certainly make our life easier with this conversion, right? Because we could go, instead of fluid ounces to gallons to liters to milliliters, we could go straight from fluid ounces to milliliters. Skip all that other nonsense. Let's try that. 12 fluid ounces. And now we have an equivalence that gives us fluid ounces to milliliters. So those are one, and then this new relationship that we have tells us that there are 591 milliliters in 20 fluid ounces. If you multiply 12 by 591 and then divide by 20, do you still get the same number? Or something really close? There may be some rounding slight differences, but it should be pretty close. What? 354? Yeah, so pretty close, right? Within some rounding errors there. Because we don't know how precisely the 20 is and all of that. So your relationship that relates one variable to another doesn't have to necessarily have a 1. You could have so many of these per so many of these. All right, so please keep working on the homework with this. Chapter 2 now we're done with. Please make sure you complete that homework. And then now into chapter 3, looking at some matter. If you want to work ahead a little bit in chapter 3 and start looking at energy and temperature stuff, that would probably be good. We'll get into that on Thursday. If you come up against places in the homework where you get stuck, please bring those into class and ask at the beginning or whenever we get time, or you can ask up in lab. There's usually time for that. So let's head up to lab. We'll start at 2. Please make sure you got your pre-labs ready to hand in at the beginning, and that you're, looks like most people are dressed appropriately except for the couple people I talked to. Yeah. I don't collect the homework, no. But I'd be happy to look at it and go over it with you or whatever. Yes, right.